When, good morning, good afternoon, good part of the day, everyone. Welcome to the largest, fastest growing, and the most active, now have gone viral and global large-scale Scrum community. And today we have a very special speaker that I would like to do a proper introduction to. His name is Dave Farley. He's from the UK. He is a very engaging and entertaining and knowledgeable speaker. He's the pioneer of continuous delivery, a thought leader and expert practitioner in CD, DevOps, and test-driven development, as well as software design. Dave has been the early adopter of agile development techniques, employing iterative development, CI, CD, and significant levels of automated testing. He worked in large-scale distributed systems and has a very long track record of creating high-performance teams, as well as shaping organizations for success and creating outstanding software. Dave is also managing director and the founder of Continuous Delivery Ltd., one of the authors of the Reactive Manifesto, and the winner of the Duke Award for the open source LMAX Disruptive Project. He is also the one of the best sellers. His books are one of the best-selling books, specifically on continuous delivery and modern software engineering. So without any further ado, Dave, I would like to pass the baton over to you. Please take it away. The floor is yours. Everyone, could you kindly please keep your cameras on if you can and mics off. And Dave, please take it away.
Thank you. And hello, everyone. Nice to meet you all. So the things that really interest me about software development are the things that feel like they're durable, the things that help us to do a better job, no matter what the job is that we're doing. And I've come to think of some of those things in terms of being the foundational principles of a genuine first-class engineering discipline for software. One of the things that I mean by that specifically is, and certainly is the heart of my book, Modern Software Engineering, it's the practical application of scientific style rationalism to solving problems in software. And I think that's what this is about. And that's what I want to talk to you about today. So let's begin by talking a little bit about what it is that I think want to talk about today. So my theme is that I'd like to talk a little bit about what engineering actually means in general, but specifically for us. I think it's common for us to debate whether what it is that we do is engineering or not. And I would certainly admit the vast majority of my career I spent doing software development and having job titles like software engineer, but I wasn't doing anything like engineering at all. Later in my career, I started working in places that didn't like the term engineer, and so I tended to dislike the use of the term software engineering as well. And then later still, I did some very hard things that required us to do what I now think of as software engineering to make them possible. And I learned a huge amount in doing that. And that's really the foundation of my thinking about what really works for software development these days. So I think that there are some common foundational principles that are generically true. Whatever the nature of the software you're building, whatever the nature of the companies that are employing you to do it, whatever the technologies that you choose to use, if you're building COBOL or embedded systems, or you're coding things in Rust or web pages in TypeScript, doesn't matter. These principles apply. And they'll probably be somewhat familiar to you, but these are the things that I'd like to talk about. And I'm going to identify 10 of these guiding principles that I think, if we follow them, guarantee a better chance of success. They don't guarantee success because nothing does. But if you do these, you will have a better chance of succeeding than if you don't. And there's data to back that up as well, in the form of the Accelerate book and the State of DevOps reports over the years. But we'll talk a little bit about those. And I want to demonstrate those, looking at those in the the context of other engineering disciplines, and then talk specifically about what happens when we apply those to code. So what is engineering? And I think we often make several mistakes when we start to think about software engineering in particular. So in other disciplines, engineering is rather simply the stuff that works. Certainly modern engineering is kind of the practical application of science to solving practical problems. And if something doesn't work, we change it until it does. And then that's the modern version of engineering. So if whatever it is that we're doing isn't working, it's not engineering, kind of by definition. Software is I think, one of the more difficult things in its nature that we do as a species. It's got some really quite esoteric aspects to it. And there are some kind of quantum level physics difficulties when we start talking about ideas like concurrency and shared state in different processes and so on. This is really difficult stuff. So I think that applying a more disciplined approach to development, a more engineering style approach to solving problems in software is important for us. And I think that's really the stuff that works for us. I've been talking about engineering and ideas like that now for several years in public. And so I get involved in quite a lot of conversations about it. And one of the forms of conversation that I get involved in quite a lot is conversation about bridges. People say, Dave, that's all very well, but what we do isn't bridge building. And of course it's not bridge building, but I think that's mistaking bridge building in several important ways. So first of all, bridge building is probably a lot more complicated than we give it credit for. Certainly if we're building a brand new kind of bridge that's never been built before. Bridge building is not some cookie cutter exercise that you can perfectly plan with a Gantt chart. Things will go wrong. The ground will be softer than you thought in one place than another. You'll have to change your plans. You'll have to react to what's going on. You'll have to try stuff out. These are the reality of what engineering in any discipline is really like. But one of the things that we can certainly say in looking at other engineering disciplines is that they're not all the same. There are some common themes when we talk about engineering, because the stuff that works tends to be scientifically rational, a term that I keep coming back to, but it tends to be, there's some maths involved, there's some scientific philosophy at least involved, and there's the practical, pragmatic approach of just identifying and preferring the things that really work rather than the things that we like doing. And that's true about all different disciplines of engineering. So one of the things that we can probably say about software engineering is that whatever it is, there will be aspects of it that are unique to us. That's true of every other form of engineering. Aerospace engineering is not the same as chemical engineering, which is not the same as electronics engineering, and so on. So I'm going to pull some examples from the car industry, the aircraft industry, and the space industry. And I'm going to mention Lego along the way as well as part of some of my examples to demonstrate these concepts. So what does all this mean for us when we start to think about this in terms of software? What is engineering really in terms of our use of it? This is my working definition. So when I use the term engineering, if you've got anything else in your head, try and hold on to this for the rest of the talk at least. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. That's what I mean by engineering when I talk about it. Something very, very specific. To put this more simply, engineering is how we as a species solve the hard problems. I would say that engineering is kind of the pinnacle of human creativity, because as well as it requiring ingenuity and creativity, it also requires some science, and ultimately whatever it is that we're doing has to work. So there are additional constraints on our creativity when we're talking about engineering that don't exist in other forms. If I'm making a piece of music or a piece of art, that's a different kind of creativity and certainly creative, but it's no more creative than engineering. And in addition, engineering has to work. So I think it's a mistake to confuse craft with creativity, which I think is a mistake that we often make when we're talking about these things. The other thing I think is that's important to remember is engineering is really the foundation on which our high technology culture is built. So despite the catastrophe today that has been going on with the Microsoft Azure problems, engineering is the foundation of pretty much everything around us. Wherever it is that you're sitting, unless you're sitting in a forest somewhere, if you look around you, pretty much all of the stuff that surrounds you is the fruit of modern human engineering in one form. I'm sat in a chair that was engineered. I've got a wooden table in front of me, which was also engineered, as well as all of the electronics that are surrounding me. So this is the basis of our high-tech culture. And so I think it's important to not miss it. That has an impact on our civilization, really. And this is a bit grandiose, certainly, but this is a graph. This is not my graph. I took it from somewhere else, but this is a graph that's meant to roughly put technological advancement on a timeline. Human beings have existed as a distinct species for somewhere between 200 and 300,000 years. And for all of that period, not very much happened. Then only around 500 or 600 years ago, something started to happen. And pretty much all invention has happened since then. This is where science started. So science kind of lit this touch paper of explosive growth of knowledge and understanding and technological advancement. Here's another similar kind of exponential graph. This is based on the work of Buckminster Fuller in the 1980s, who got interested in the rate at which humanity accrued knowledge. So he went to work estimating the rate at which human knowledge doubled. And he found that in 1900, all human knowledge doubled about once a century. By 1945, knowledge was doubling every 25 years. By 1982, it was doubling every 12 to 13 months. More modern predictions, Buckminster Fuller's dead now, but other people have taken on the work. More modern predictions suggest that all human knowledge is doubling at a rate of every 11 to 12 hours. Now, I'm a little bit skeptical about that last one. That's a rather extravagant claim. But even so, there's certainly this explosive growth. And we're kind of aware of that. If you think of all of the information, the knowledge that is being generated by us and the AIs that we create, the data that we're accruing from computer systems, certainly something important is going on. Science was invented somewhere down there, and computers and software were invented around here. So the stuff that we are thinking about, the stuff that we are doing, has had a profound influence on the world that we inhabit. Which brings us on to the next question I think that's interesting to ask when we're thinking in terms of engineering. So what is it that engineering is really for? And I think this is another of those things that we tend to get wrong. I think that we often make an assumption that engineering is a kind of cookie cutter process that defines the one true solution. But that's not it at all. It's almost entirely the opposite of that. Engineering does not define a solution. What engineering really does is it works to rule out the bad solutions. Engineering is the stuff we identify the stuff that doesn't work, rule that out, and we end up with a whole range of solutions that might work. And then the creative part is to choose the solution that we prefer of the set of things that is possible, that might work, ruling out the stupid ideas that don't work. And I don't think we do enough of that in software. I think we're tend to be a little bit too accepting of ideas that we kind of tried lots of times and have never really worked. Waterfall development is the one that comes to my mind. I don't think there's any reason why waterfall development is ever a better choice than other ways of working. The last thing that I'd like to mention in terms of the things that we tend to get wrong about engineering is that we tend to confuse it with production lines. And production lines are about solving a different thing. Often, one of the pushbacks that I get when I'm talking about engineering in the context of software development is that ours is too creative a process, and it's not kind of a cookie cutter process that leads to a specific outcome. I've already talked about that's not what we really do, but specifically, that's not what engineering really does either. In all of these pictures, the engineering happened before. This isn't engineering. These are production lines. This is the repeated process of trying to develop a product that was engineered earlier on a repeated basis, so we can create many clones of the same thing over and over again. This isn't our problem. This isn't ever the problem of software, because the economics of software mean that it would be stupid to work this way. We don't have a production problem because our job is very different. Our job is to come up with a description of some ideas that we can then crystallize into the form of a stream of bytes that represents the system that does something useful for us. And once we have that stream of bytes, the unique property of digital assets is that we can clone them perfectly, essentially for zero cost. Almost however big that stream of bytes is, we can copy it perfectly for almost no cost, which means that we never have a production problem, because the production of a stream of bytes is simply copying it. So our problem is the initial design. Our problem is the initial creation of that first ever stream of bytes. And after that, production is trivially simple. So this is a very different kind of world to the world of making physical widgets. Engineering then, certainly software engineering, is about exploration and discovery. So software development is about exploration and discovery. And so they are a good match. So what's the stuff that works for us? I think it divides into two categories. I think in order to be able to take advantage of this line of reasoning, then what we need to do, if software development is all about exploration and discovery, then we as a profession need to become world experts at optimizing for learning, because that's fundamentally what our job is. Our job is not to write code. Our job is to solve problems with code. And for that, we need to learn what the problem is. We need to learn what solutions might work for our problem and try them out. And we need to learn whether our solution actually fits, our design actually works out in the end. All of those things. So we need to do things that allow us to learn. And the systems that we built, the modern systems that we build, are bigger than the capacity of any single human's head. So we need to be able to organize our work and our thinking to manage the complexity, so that we can build systems that are more complex, that we can hold in our heads. And so those are the tools of our trade. Those are the foundations on which I think our discipline should be built. And I've got 5 things in each of those categories, and the rest of my talk I'm going to explore those in a bit more detail. So in order to optimize for learning, we need to work iteratively so we can try things out. We need to be experimental so that we can try things out. We need to gather feedback so that we can evaluate our experiments and understand the success or failure of our choices. Software development and engineering really is an incremental process of growing our products in small steps and evaluating our ideas after each small step. And engineering is a deeply empirical discipline in that it's reality driven. Whatever works is what's important, and things that don't work we should rule out, and the real world is going to teach us some of those things. So we need to be good enough at learning to be able to evaluate what's going on in the reality of our systems and react to that, change our systems on the basis of what we learn. So let's look at each of those in turn with some examples from other engineering disciplines to try and put them into place. This is a picture of the Wright Flyer. This was the first heavier than air, powered, human carrying, controllable flying machine. I've made all of those caveats because there were versions of flying machines that did some selection of those things, but never all of them together before this thing. This first flew on 17th of December 1903, and this is the picture of the first flight. And the Wright brothers kind of had the monopoly for some time after this first flight. They were the only people that were able to fly to any significant degree. Everybody else was playing catch up. But probably for around about the first 2 decades after that first flight, these things were death traps. Most of the people that were pioneers in the early aircraft during this time were killed by the things that they were pioneering in, including one of the Wright brothers, who was killed in a crash of an aeroplane very similar to this. So what happens in engineering is iteration. It might be in physical engineering, like aeroplanes, it might be slower than we're used to in software, but nevertheless, it's iteration. So after each accident, that was inspected and looked at, and lessons were taken from it, and they were applied to the next generation of aircraft that were designed. This aircraft is a Douglas DC-3, and it's from about the age of the Second World War, the start of the Second World War, and it was really one of the first recognizable passenger carrying airplanes. There were passenger carriers earlier than this, but this was the first one that made it practical. It's an American design, and it could fly people at hundreds of miles an hour in reasonable levels of comfort, and is more close to being more recognizable as a passenger carrying aeroplane. But even so, you know, it was a bit slow, they were a bit bumpy, very expensive to fly, very weather affected, and so on. So we continued evolving, and we end up with something like this. In 2017, commercial aircraft flew the equivalent of 2/3 of the population of the planet, and there were no fatalities. That's the first time that ever happened. And I know it's trite to say it, but what that means is that you are safer in a commercial airliner statistically than we are sat here talking to each other today. We're more at risk sat at home or in our offices than we are in an airliner, according to the statistics. It's a remarkable safety record that took over 100 years to achieve through iterative change, iterative and incremental change in the design of systems. That is what engineering does. That's what engineering does across the board. That's getting to that. If it doesn't work, we change it. And that's how engineering works. Iteration, though, philosophically, mathematically, really, is a more profound idea than we often think about it. If we have a goal of some kind, then iteration is the way to hit the target. And the way that you do that is that you come up with a goal, and then you decide wherever your starting point is, and you establish some kind of fitness function, a measuring stick that tells us whether after each small change we are getting closer or further from the goal. And then you start, even randomly, trying stuff out. So we could try out an idea and see whether that got us closer to the goal. This one doesn't, so we could discard that idea. And then we could try another idea. And this one gets us a little bit closer to the goal on our fitness function. So we could keep that idea and we could move on, establish a new starting point. And we keep doing that. We keep iterating step by small step. And the smaller the steps, the less risk we take of missing the goal. And this is the way that we are guaranteed to hit the goal. Even if the target moves, we can change the fitness function and this still works. This is much dramatically more effective than trying to hit the goal in the first shot. And so working in these small iterative steps is a profoundly different and important way of organizing our work to more reliably, more effectively be able to achieve whatever the goal that we set for ourselves. This is how machine learning works. This is how evolution works, really. This is important stuff. The next thing that we need then is feedback, and feedback is the measurement that we use to figure out whether we're getting closer to or further away from our goals. And this is important too, because if we think about how to solve problems, often we get seduced by kind of the illusion of rigor. You know, if we think really hard and we do some hard sums and some maths, then it must be right. We must be more correct than if we do more ad hoc things. Well, maybe, but not always, and not really. So let's imagine that we were challenged with balancing a broom. We could do it the waterfall way. So we could try and analyze the center of mass of the broom and work out where that is. And we could remember from our physics lessons at school that in order to balance things, we need to line them up so that the center of the line from the center of mass, the fall line, the gravity line from the center of mass lines up with the point of contact of the thing. So we could figure out whether that's right, that's not right. So we could reorganize the broom and we could position it so that the point of contact with the floor goes through the center of mass of the broom. And then we could precisely position the broom so that there was no little impulse left, so that it wasn't traveling one way or another when we let go of it. And if we got that perfectly right, the broom would balance. There's a weird Japanese art form of balancing strange things on each other. So human beings can do this, but essentially to be able to balance things in this way, there's only one solution to this problem. This is not how you or I would balance a broom if we were challenged to do so. What we'd do, because it's not stable, what we'd do instead is we'd do this. We'd pick up the broom. We wouldn't bother caring where the center of mass was, at least not measuring it. We'd pick up the broom, we'd put our hand in place, and then we'd use feedback. If the broom started tipping one way, we'd push our hand away from towards the direction that it was tipping, and so overcome that. And so by reacting, gathering the feedback and reacting to what's going on, we get a much more stable solution. This is so stable, in fact, that if I was balancing a broom and somebody came along and pushed me, I could make a big move and react and carry on balancing the broom, or I could make tiny little moves and keep it very still indeed. This is very powerful, and powerful enough that this is how space rockets work. So the way that space rockets work is that they gimbal the motor. They have sensors in the rocket to determine how much it's tipping, and they steer the motor to overcome the tip if it starts tipping. And this is very efficient. It does this thousands of times a second, all software controlled these days, of course. And that's how you take off or land a rocket. The next in my list of 5 things is incremental. And this is a picture of the first module of the International Space Station. Now, I guarantee you, when the International Space Station was initially thought of and designed, they'd got a rough plan of what it would end up with. And over time, they'd add pieces bit by bit by bit until they end up with the International Space Station as we'd recognize it today. Except that's not exactly what was planned. It's close in some in some regards and very different in others, because over time, incrementally, as the space station grew, choices were made, changes happened, design requirements came along, technology advanced, and so the design changed. There are pieces in the International Space Station that nobody could have envisaged when they started building it. That's another feature of engineering. It is inherently incremental. If you think of almost anything that is a human engineered device, it's different now to it was 10 years ago, and it was different then to what it was 10 years before. Think of an iPhone and an early iPhone compared to the one that's probably in your pocket. The next in my list of 5 things is being experimental. And often people see this as being scary because it paints a picture of the experiment being wrong. And while I don't see that as scary, it's true. Experiments can go wrong. And if they can't go wrong, they're not really experiments. But I would put it another way, is if that we're not risking something going wrong. If our experiments don't go wrong, then we're not actually learning anything. Jeff Bezos, amongst many things that he has said about experimentation, has said that if 50% of Amazon's experiments don't fail, they're not trying hard enough. They're not risking enough in their experimental approach. Experimentation is really the only way in which we can make progress. Experimentation allows us to make controlled progress, so we can take risks, but we can control the risks so that they're not fatal. My guess is that the software disaster that happened today wasn't thoroughly enough tested. I don't know that. The details haven't come out yet. But if it was, I think there's a chance that they would have caught it easily. Certainly, there are ways of controlling the risk. Treating the release of this change that broke industries across the world as an experiment would have resulted in a more controlled way of dealing with the risk, and so a better way of mitigating those risks, and so would have at least limited the impact of the failure when it happens. So working experimentally is a lot about working to control the variables so that we can learn from our experiments. We can take control, and there's a wide range of applications of that in terms of software development. So we can think of things like version control systems, or we can think of things like infrastructure as code. We can think of things like automated testing or A/B testing in production, or canary releasing to release things more safely into production. All of these are ways of controlling the variables and to carry out experiments in safe, controlled manner. One way in which this has happened in the aviation industry for a very long time, practically, physically, is that there's a rule. If you want to create a new aircraft with a new engine, you don't just go and fly the new aircraft with the new engine. What you do is that you start with an old aircraft with an old engine, and you take the old engine off, and then you put the new engine on, and some brave person goes and flies this, and if they come back alive, then they consider that a success, and then they can move on in their experimentation. So they're controlling the variables. Then the next step is you try the new aircraft with an old engine, and another brave person goes and flies this, and if they come back alive as well, then now's the time to try the new aircraft with the new engine. This is practical, pragmatic experimentation. The last in my list of 5 things for optimizing for learning is working empirically. Here's another picture of an aeroplane. I think this is the last picture of aeroplanes, so if you don't like aeroplanes, you'll be pleased to hear that. This is the first commercial production jet aeroplane. This was a military aeroplane built by the Germans in the Second World War. This is a thing called a Heinkel, and it was the first production jet aircraft. And you can see it's kind of unusual if you think about how most modern jet aeroplanes look, in that it's got the big wheels at the front and a tiny little wheel at the back. This is what pilots call a tail dragger uh, configuration of an aircraft. And the reason for this design choice is because if you've got a huge engine with a big propeller, which is what all aeroplanes had up until this point, then you need to make room for that big propeller up the front of the aeroplane. And so tipping the nose of the aeroplane up in this way, even though that makes the airplane more unstable on the ground, is a good choice for a propeller-driven aircraft with a big propeller engine. So they built the first jet airplane in the same way because that's what they were used to doing. Then they went and flew it, and the jets point, as you can see, the jets pointing at the ground, so it melted the runways, which wasn't a great idea, really. And so they learned from that, and from then on, all jet aeroplanes are built with what's now called a tricycle undercarriage, which moves the main wheels a little bit further back so they're behind the center of gravity, and puts a small wheel at the front instead of at the back, so that the airplane sits with the fuselage horizontal to the ground, and so the jets are pointing horizontal to the ground and don't melt the runway. That's practical empirical learning. And that's always a part of engineering. Stuff doesn't go as we expect. As the people at, I've forgotten what they're called, CrowdFrame or whoever it is, the people that have been, that did the security fix that blew up all of Microsoft's stuff today, as they are probably thinking, the real world doesn't go as we expect. That's not unusual to software. It's a feature of engineering, and it's, in some ways, it's a positive feature if we can do it in controlled circumstances. This is a picture of SpaceX's Starship, the biggest space rocket ever, that is aimed to be a reusable space rocket, taking 100 tons at a time to and from Earth orbit, and allowing us to go and live on Mars one day, maybe. But at the moment, SpaceX is the most successful space rocket company ever by miles. If you add up all of the launches, all of the payload that every other space rocket ever has launched into space, it's nowhere near as much as SpaceX has launched with their reusable rockets. And there's a reason for that. And part of it is because they do empirical learning. They move really fast and they try stuff out and they learn from the mistakes. This is how engineering makes progress. And you have to do it. If you're doing this with space rockets, it's quite expensive. But this is how we learn. We try stuff out, see what works, and keeps the stuff that does, rejecting the stuff that doesn't. The next problem that we need to solve is the complexity of modern software systems. Modern software systems are vastly complex. The picture labeled Amazon here, this is a picture of microservices in the Amazon cloud running the Amazon system. And if you see this as an animation, which it is, then it looks organic because it's so fluid and it changes so much. Modern software is often complex. So software development is about learning and managing complexity. So 5 things for managing complexity, and these will be familiar to you, but what I mean is not just that these are good ideas, but what I'm saying is these are tools that we can use in order to be able to improve the quality of our software and managing the complexity of our software. They are modularity, cohesion, separation of concerns, abstraction, and coupling. So let's look at each of those in turn too. So modularity is about dividing systems up into modules. I lied to you. Sorry, I was mistaken. There is another aeroplane. This is the last one. So we can design systems as modules, and that's a good thing. If the in-flight entertainment system fails in a modern airliner, it doesn't stop the engines working. That's a good thing. It's not a thing that we can always say about software, but it's still a good thing if we design systems to be suitably and appropriately modular. another form that's a bit closer to home. This is a modern iPhone, and even though this is a incredibly cleverly engineered device and very tightly related pieces, even so, each of these pieces has one job and does that one part of the function of fulfills that one part of the function of a phone independently of other parts. And that's a good design strategy. A little bit closer to home still. If you can see me on the screen, I don't know if you can at the moment, but I'm very old and I've been writing software for a long time. And when I started writing software professionally, if we wanted to print something out onto a printer, we had to know the make and model of the printer that we were writing to, because that's how it worked. And if I wanted to print things out on an Epson FX80, that was different to the codes that I needed to send to an Epson RX80. And sometime later, the operating system vendors decided that that was not a great way to do things. So they came up with an abstraction for printing and made that abstraction concrete in a way that we could introduce the use of printer drivers and build modular systems, modular operating systems that we could extend with new behaviors without changing other parts of the operating system. So now we can print to our hearts, we can write software that's able to print even when we have no idea what the printer will be, because we can use those abstractions as a point of contact to say what it is that we want to print. We've separated the responsibilities here in terms of the design of the system. Here's another form of modularity. This is a nasty piece of code, and it's written in C, but just because it's written in C doesn't mean it has to be nasty. You can write nice C code as well if you try hard. In this example, there's 361 lines inside this if statement. The most common feedback that I get when I show people this piece of code is, oh, we have much bigger if statements than that, which I don't think is a good thing. This is what it looks like in the context of this method. So let's take a bit closer look at this. The if statement says if unlikely bang CI. So I assume everybody knows what's going on now in this code. Maybe not. I did the work for you. I had a look at this code to try and work out what was going on. And I think that what they meant to say was this. If there's no connection represented by CI, create a connection. That's it. I think that's what all this if statement does. And if we simply did that, if we simply refactored the code to make it more modular, like this, then that's better code. I hope you'd agree. That's now it's more readable, it's easier to change. We could change the way that the connection works and so on. It's just better. It might not be good still, but it's certainly better with that increase in modularity. My favorite description of software design comes from Kent Beck. And he said that good design is about moving the things that are related closer together and the things that aren't related further apart. So modularity is really about moving the things that aren't related further apart, and cohesion is moving the things that are related closer together. If we organize our software in that way, then it manages the complexity in very, very useful ways. It's easier to reason about, easier to understand, easier to change, easier to test, and so on. The next in my list after modularity and cohesion is separation of concerns. And on the screen is a picture of a modern electric BMW. And BMW, like several other car manufacturers, have made an interesting choice to separate the concerns of the mechanics of the vehicle from the utility of the vehicle. So they've built a platform that includes the steering, the wheels, the braking systems, the batteries, the charging systems, the electric motors, the electronics management systems, and so on, all of that stuff. But they've separated the shell of the car and the parts that we kind of use as a tool to do things. So if you want a sports car, you're going to get the same chassis and electric motors and chargers and steering system, but you'll have a sports car chassis. And if you want an SUV, you'll get an SUV chassis. And if you want a sedan, you'll get a sedan chassis, and so on. So this is a practical example of separating out the concerns. This gives us flexibility in terms of the design. This is my favorite picture of a car. This is obviously an ancient car, and there's very little abstraction going on here. If you look very closely, and certainly if you're of a mechanical mind, you can pretty much work out how all of this works. You can pretty much see it. It's there in the open for us. This thing here, I'm pretty sure, is a combined control that does both the braking and the acceleration of the car. This thing here that looks like a tiller is a tiller, and you can see that it's kind of connected to that vertical post, and that if you follow the vertical post down, you can see that there's a little crank at the end and a little push rod that goes to the front wheel, so that when you move the tiller, it rotates the post and that moves the crank, which steers the steering wheel. So it's clear how this thing works. What happened, though, over the evolution of the cars is that we started to abstract things. We started to standardize the controls, make them more common, and move away from the kind of exposed no abstraction that was exemplified by this very old car. In the middle of the picture here is a modern steering wheel from a modern car. So how does that work? Well, just think about that for a moment. How do you think that steering wheel works? You can't tell. And that's a good thing. You don't need to tell. But it could be all sorts of different ways that it works. It could be mechanical, could be parallelogram steering, rack and pinion steering like that. It could be power assisted with constant velocity joints and hydraulic pressure moving the wheels. Or it could be a modern electrical system that's rather like a joystick in a computer, where there's some kind of rheostat measuring the voltage in a resistance coil and sending signals, computerized signals, digital signals, to some servo motors that actuate the steering of the wheels for the car. We can't tell, and we don't care. That's what abstraction gives us. It allows us to interact with a different part of the system without caring about how that other part works. And that's a deeply important idea. Let's look at that a little bit more closely in terms of software. So here's two pieces of software, a blue bit and an orange bit. And it's doing all these things. They're going to initialize the orange bit. It's going to report that it's been initialized. We're going to get a delivery date, and it's going to return the delivery date, get some VAT, calculate the total for an order, and tell it what the ordered items are. And then it's going to confirm that it's placed the order by going and looking in the shared database. This is horrible. This is a horrible design, clearly. There's no abstraction really, or very little abstraction going on here. How much better then if we did something like this instead? We abstract the conversation, so we're placing an order and we confirm that the order's placed. There's probably a lot of the similar data that's involved in this conversation. It might be allocated differently though, because we are now telling the blue thing is telling the orange thing what to do, and the orange thing is just sending an event saying that happened. This is a cleaner design, a more abstracted design, a less coupled design as a result of that. Each part of our system should keep secrets from every other part of our system. I'm speeding up a bit because I'm conscious that we're getting close to the end of our time. I'm sorry. Another way of looking at this is from a point of view of coupling. So here are two differently coupled systems. I'm the proud grandfather of three gorgeous grandchildren, and I often play Lego with my grandchildren, and my granddaughters will make something from Lego and say, "Look, Grandpa, do you like this?" And I'll say, "Oh, yes, it's wonderful. What is it?" And they'll say, "It's a giraffe." And I'll go, "Oh, yeah, of course it's a giraffe. It's a wonderful giraffe." They can use their imaginations. They can build anything they like with the Lego bricks on the right-hand side. The Lego bricks on the left-hand side are very, very different indeed. They build one thing, and each brick has its position. If you don't put that brick in that position, you don't get to build anything really. You can't even build a Maserati with this kit because it's meant to build a Ferrari. This is so coupled to the solution. There's one way of putting this together. It doesn't allow my granddaughter to use those pieces to build a giraffe or a submarine or a spaceship or whatever else they want to do. So these are differently coupled systems, and coupling, it's not right. One of these isn't right and the other one wrong, but understanding which one to use under what circumstance is deeply important to the management of our systems. I would regard coupling as one of the more challenging things that affects our ability to build software, certainly complex software and certainly complex software at scale. It's coupling that's the difficult part. Everything else is easy, but managing the coupling is the hard part. And so making decisions about that with a preference on the whole towards looser coupling where it makes sense is very sensible to be able to do these things. Let's just look at this again, what we can do to manage that in terms of software. So once again, our blue thing is doing all of these things. And in this case, the orange piece has changed the date format. And that breaks the system because these things are tightly coupled as a result of the lack of abstraction in the way in which they exchange information. Now let's think about the other design choice that we made. So supporting our place order approach, we could build a little translator, a little adapter between the orange service, whatever it is, and the blue service. So when the blue service says place order with an old date, the orange service can say, oh, I know that you're talking in the old version of the API. So I'm going to respond in the old version of the API. So now these two are more robust. They're less coupled to one another. And as a result, our system overall is more robust and more flexible. So let's just think about this for a moment of applying these guidelines. So we've got our 5 strategies for managing complexity: modularity, cohesion, separation of concerns, abstraction, and coupling. My argument, as I said, is not that generically these are good things, but what I am saying is that if you adopt the discipline of every time that you have a choice in the design of your software or the implementation of your software, choose the one that improves the modularity, choose the one that improves the cohesion, choose the choice that improves the separation of concerns, so each part of your software only does one thing and does it well. Choose the one that increases abstraction so that you know less about the pieces that you're interacting with. Choose the one that reduces the coupling. And if you do those things, my guarantee to you is that your software will be easier to maintain, easier to change, easier to work with. You will have managed the complexity as a result. And please notice, I haven't said anything at all about the nature of your code, the nature of your problem, the nature of the industry that you're working in. These are generically true, whatever the software that you're writing. I don't think we think about these things enough. I don't think we practice them enough in most of the software that I see. This is more than just motherhood and apple pie.
Steve, quick time check. We had the hour. Unless you're willing to take a few extra minutes, we may expect people dropping now.
I'm happy to take a few extra minutes, but I'm conscious I don't want to be imposing on people. So I'm also happy. Let me just skip forwards and I will talk. I was going to show you some code that demonstrated the application of these things. I'm just going to skip forwards to here, and I'm going to take 2 minutes to wrap up, and hopefully then, if anybody wants to stay around, you can ask questions while other people are disappearing. So I'd like to challenge you to just do 2 things. Think about a software system that you're familiar with, a current one that you're working on, or one that you worked on in the past, perhaps, and now think of 2 versions of it. Think of the first one, which doesn't optimize for learning. So you didn't start working iteratively, you didn't gather feedback, you didn't work incrementally, you didn't carry out experiments, you didn't learn empirically as you went, which means that the only way that you can build this is to make all of the choices right and get them perfectly right first time. You're not going to be trying anything out until you're not going to find out until the end and it goes into production that you know that that works. I've worked on projects that look like that, big waterfall projects in the past. They look like that and they don't work. The chances of success of that are almost zero. Now imagine a version where you were trying things out in small steps, and after each small step, you were gathering feedback and you were evolving the system small step by small step as a series of small experiments, consciously designing the feedback to match the experiment, controlling the variables so that you'll understand the results of the experiment, and learning from your system in production and in use and in test and all of those things. Which one of those is going to be the nicer project to work on? I guarantee you it's going to be the second one. Now imagine two versions of a piece of software that's taking different strategies for managing complexity. One of them has no modularity. There's no cohesion. Code is spread doing the same things in different parts of the code. There's no separation of concerns. The whole code base is in one big mess, in one big lump. There's no real abstraction that separates one piece from another. All of the pieces are tightly coupled together. This second version, this version is so common, we have names for it. This is a big ball of mud or spaghetti code, or sometimes it's what we call legacy systems. Now imagine one that is modular, cohesive, good separation of concerns, well abstracted so that it's easy to understand what each part of the code is doing, and loosely coupled where that's appropriate. Again, which one would you prefer to work on? Which one's more likely to be successful? And once again, I pretty much guarantee you that you'd prefer to work on the second one. And again, I haven't mentioned technology or industry or anything else. These are just generically true about software development, as far as I can tell. I don't believe the only way that we built waterfall software successfully in the past was by cheating the waterfall and basically hiding working iteratively. It was certainly the way that all the teams that I ever worked on did it. So all of these things matter for one reason, though. They allow us to change our software, and that's deeply important. Change is inevitable, and there's all different kinds of change that will impact on us and force us to rethink. Some of it's possible to plan for, some of it's not, some of it's literally impossible to plan for. But stuff changes all of the time. And so being able to cope with that is essential. I would argue that we ought to adopt the notion that the only thing that matters in terms of the quality of a system is our ability to change it. Now, that might seem weird because, of course, things like security and resilience and scalability and durability and all of those things matter. But if you can't change the system, the only way that you can get any of those things is by getting those things perfectly right first time. So optimizing to maintain our systems in ways that make it easy for us to change the system is how we get more secure systems, is how we get more scalable systems, is how we get more robust systems, is how we get systems that adapt to better meet user needs as user needs change. This is how we build great software. Right, I'm very sorry that I slightly overran. I'm very happy to hang around for a while and take any questions that are around, but I also thank you for listening today. And if anybody wants to disappear, you're very welcome to.
First of all, Dave, before everyone jumps, I want to, and I do encourage people to stick around for a little longer if they can. I want to thank you personally for taking the time and coming out and doing this for us. That's great.
Pleasure.
More thanks from me personally, but go on, folks. Anyone has any questions for Dave? Any comments? You know how to find Dave. Obviously, he's displaying his contact info on the screen. Also, he's pretty transparent and visible on LinkedIn. So I'd strongly recommend looking for his profile and connecting and asking questions. And he's got a great YouTube channel, if I'm not mistaken, Dave, right? So you have lots of stuff going on there. So this will actually end up on my channel, but you can certainly repost it. Any other questions? Anyone? Going once? Twice. Well, I guess there are no questions, so I want to thank everyone for joining, participating in by being present, and once again, Dave, thank you very much for your presentation. There's some questions in the chat that were posted earlier, or were they just comments? So I'm not too sure. I'm just scrolling back up a little, mostly comments. So okay, so we'll just then call it a day. So once again, thank you very much. I'll do
Pleasure.
and if you could just share with me your deck so I can make it available.
Will do. Okay.
Great
Thanks.
weekend, everyone.
Bye.
Be safe, stay safe. Thank you.
Bye.